so far we have seen different measures of dispersion, which were range, IQR, and variance. Now, these measures are good to deal with one quantitative variable. Suppose you have height of a group of individuals, then you can use variance, you can find the variance, or you can use IQR as per your problem. But if you want to compare the variation in two different processes, then using coefficient of variation is a better choice. Why? Because it is a unit-free statistic, and the higher the value is, the greater would be the dispersion. And it is calculated with this formula, which is sigma by mu, which is standard deviation divided by the mean. So here, whatever the unit is, it will get cancelled out, and that is why you have a unit-free statistic. So let us see an example to understand it. Suppose you are in the market for a mobile data plan and you are deciding between two different providers, say A and B. So you are interested in determining which provider offers a data plan with less variability in pricing. And to make an informed decision, you take plans from each provider, you calculate their means and standard deviations, which are as follows. So for the first provider, the mean price is 320 and the standard deviation is 45, whereas for the second one, the mean price is 180 and the standard deviation is 30. Now, if you just look at the standard deviation, you might feel that since standard deviation for B is less, that is 30, so there would be lesser variability. However, let us try to calculate the coefficient of variation and see what is the answer. So, coefficient of variation is sigma by mu. So, sigma is 45 divided by mu, which comes out as 0.14, and the other one, it comes out as 0.16. So, in fact, you see that the first provider has less variability. Thus, you can conclude that provider A offers a data plan with less relative variability in pricing. So this reflects the significance of coefficient of variation, because when you are comparing two different processes or methods, then in that case, standard deviation alone would not play much role. It would not be able to give you the correct information. Instead, coefficient of variation would provide you the correct answer. Another related concept is the z-score, which makes use of standard deviation and mean. So I have included it over here. So basically, standardized z-score is the number of standard deviations it falls above or below the mean. So if you are given a mean and standard deviation, then the z-score for an observation is nothing but x minus mu by sigma. So what you are doing is, you are basically standardizing the data set. So whatever the values are, it might be possible that someone has taken the measurements in inches for the height of a plant and the other one might have measured in centimeters. So you need to standardize them so that you can make comparisons between them. Now, the question is that can it be positive or negative? Yes, it can be both. So to understand that, let us consider this example. Suppose you are a meteorologist studying temperature variations in a specific region. You have data on the average daily temperature for a particular month with a mean temperature of 68.55 Fahrenheit and a standard deviation of 15.45 Fahrenheit. In this case, mu and sigma is given to you, and you find that in a particular day, the temperature is 80 Fahrenheit. Then you would like to calculate the z-score, which will be basically x minus mu by sigma. So x over here is 80, mu is 68.55 and sigma is 15.45. So you get 0.74. So z-score is positive in this case. So it tells that this observation over here, that is x is 0.74 standard deviations above the mean. Likewise, if suppose the temperature on another day you find that it is 60 Fahrenheit, then what will you say? The z-score in this case will be 60 minus 68.55 divided by 15.45. So basically what you get is minus 0.55 in this case. So you see that z-score can be positive or negative. And how do you interpret this? So z is x minus mu by sigma. So x will be mu plus sigma z. If your data point is given to you as 80 Fahrenheit and your z value finally comes out as 0.74 in that example, it means that this observation is 0.74 times the standard deviations above the mean, because you are adding something to the mean. It is 0.74 standard deviations above the mean. Likewise, if you have 60, in that case, what was your z-score? It came out as negative, which is 0.55. So here, if you see that, it is basically mu minus sigma z, right? Z is 0.55. Or you can say that it is mu minus 0.55 sigma. So this value 60 is basically 0.55 standard deviations below the mean, because you are subtracting something from that. Okay. So here we say that this is 0.74 standard deviations above the mean, and here we say that it is 0.55 standard deviations below the mean. So z-score can be both positive or negative. But the question is that is it always good to have a positive z-score? It basically depends upon the context. The sign is basically depending upon the value of x and the mean. X minus mu is in the numerator. So if x is bigger than mu, then you will get a positive sign. If the mean is more, then you will get a negative sign. For instance, positive z-scores don't necessarily imply a positive outcome, because here if you see, if you have a data where you have the cholesterol levels of a group of people, then if you get a z-score high in that case, then we know that high z-score means that for that particular observation, that particular value is basically higher than the average cholesterol of the group of people. So it means it can indicate that you have some health issue, because higher cholesterol level is not good, right? Similarly, negative z-scores also don't mean that it is referring to a negative outcome or a failure. Because if you have a data where you have the cost of production given to you and you calculate the z-scores for them, and in that case, you might get a negative z-score if the cost of production is less than the average cost. In that case, it means that you have done some cost saving over there. So, negative z-scores do not imply always that it is referring to a negative outcome. Similarly, positive z-scores also don't imply that you are referring to some success only, as you can see that in the case of cholesterol levels. So you have to identify the context of the problem and then decide the behavior or the nature of the z-score. Let us consider an example over here. Imagine you are a manager at a company responsible for evaluating the performance of two employees, Arav and Jaya, who are working in two different departments, marketing and sales. So Arav is working in marketing department and Jaya is working in sales department. The evaluation scores with mean and standard deviation values are as follows. Okay, so they conduct some exams. So in that case, the evaluation scores, their mean and standard deviations for the two departments is given to you. And you find that Arav scored 90 in the marketing department, whereas Jaya received 75 in the sales department. And now you have to find which employee performed better. So in this case, if someone just tells you that Arav has scored 90 and Jaya has scored 75, then one might think that, okay, so Arav has performed better than Jaya because he has scored more. But here is the mistake. because you are just considering their marks and you are not focusing on what is the evaluation criteria in different departments, and that varies. So for this, we need to bring them down to the same level so that the comparison of their performance makes sense. And thus we calculate your z-scores. So here, if you want to calculate the z-score of Arav, so in that case, this is x given to you, x minus mu. So mu is mean, that is 88, and you divide by 12 over here. Whereas if you look at this, the sales department, so this is x is 75, mean is 70, and sigma is 15. So let us see what are the values. So for marketing department, it is 88 and 12, and 90 is scored by 88 and 12. So, and Arav has scored 90. So if you calculate the z-score, so 90 minus 88 by 12, that comes out as 0.16. Whereas if you look at Jaya's performance, then she has got 75, and if you calculate z-score, it comes out as 0.33. So what you can see here is that Jaya has in fact performed better because her z-score is more. So if you just conclude by looking at the marks, final marks in two different exams, then the comparison will not make sense because different exams, their mean and standard deviation would vary. Different exams will have a different evaluation criteria. So it is important for you to consider the z-scores and then make comparisons to understand and gain insight into their evaluation scores. So till now, what we have seen is we have talked about the measures for categorical variables. Then we moved on to the numerical variable, where we talked about the measures of central tendency. Basically, it captured the central aspect of the data. Then we talked about the variation, that is how dispersed the data is. And last but not the least is what is the shape of the distribution, that is skewness. So skewness basically gives you an idea about the asymmetry in the data. So to understand the measures of skewness, you need to first get familiar with three terms, which are what is symmetric, the next is right or positively skewed, and you have left or negative skewness. So we will first understand the meaning of these, and then we will move on to the measures of skewness. When you have a symmetric distribution, so we know that it was going to be bell-shaped. It means that in this case, your mean will be same as median, which will be same as the mode, because mean is the center of the data. If you look at the median, median is going to divide the data into two halves. So that is why it would be in the center only at that same position. And mode also, mode is the common occurrence where most of the data falls. So the peak over here is coming at this point. So it means that for a symmetric distribution, mean, median and mode would be the same. And an example for such a data set is basically you can consider the height of a group of individuals. So height of individuals is an example for this. Next, if you have left skewed, it means that the tail would be towards the left. So to remember this, it will look like something like this. So the peak is here. It means the mode will be here. And it means here you have some lesser values. So it has taken the mean with itself and mean is coming here. It has pulled down the mean. And here you will have somewhere the median, because median is going to divide the data into two halves. So such a case might arise. So here you can see that mean is less than median, less than mode, because if you consider on an x-axis, then mean is going to the left side. So mode is the highest in this case. And when will you have such a data set in real life? In real life, we come across such situations if you consider the retirement age of individuals. For some professions, the retirement age is 60, 65, while in others, maybe if you consider the military, then in that case, the retirement age is around 45. So when it is low, it is pulling down the mean towards it. Or if you can consider an exam where the exam paper was easy and most of the students performed well, that is why your mode is over here. But still, there are certain students who did not perform well, and that is why they have pulled down the mean towards itself, and that resulting in the average of the class going down. Okay, so that is also one of the situations for left skewness. Right skewness would be if you have a longer right tail or positively skewed. So in this case, it would look something like this. So here, the mean is towards the right hand side. Mode is obviously because most of the observations are here. So mode will be near the peak, and in between you will have the median. So in this case, mode is less than median, which is less than the mean. You can consider the same example for your class, right? If there is an exam, but the exam paper is very difficult, so most of the students got around 50, while there are certain good students, suppose they have got around 95, right? So in that case, the class average will also go up, and the median would be in between because it is going to divide the marks of all the students into two halves. So these are basically your three terms, that is symmetric, left skewness, and right skew. So these concepts basically capture the asymmetry in the data set. So now, since we have become familiar with these terms, we will now move on to the measure of skewness. So the most common measure was given by Pearson. Carl Pearson gave the coefficient of skewness, which is defined as 3 times difference between mean and median divided by the standard deviation. So another form for this is you take the difference between mean and mode. So here basically it focuses on your skewed distributions, because in skewed distributions your mean and median would not be the same. Whereas if it is a symmetric data set, in that case mean and median would be the same, and this coefficient would be 0. Similarly, if mean is greater than median, in that case, you will get a positive value, and you can conclude that it is right skewed. And if it is less than 0, then the distribution is left skewed. So this value falls between -1 to 1. In the same way, you can consider the Bowley's coefficient of skewness. So what Carl Pearson did was that he basically talked about the measure of skewness, that is talked about the asymmetry in the data based upon measures of central tendency, that is mean and median. And then he also considered the measure of variation also in that to finally figure out what is the shape of the distribution. Bowley, what he did is that he considered the quartiles, because the difference between quartiles, if you recall, we have Q1, Q2, Q3, and the distance between Q3 and Q2, this distance would be the same as the distance between Q2 and Q1 if it is a symmetric distribution, correct? So you see that in the numerator and denominator, you have the same thing with just a difference in this symbol. And if you solve this, you will get Q3 plus Q1 minus 2Q2. And here Q2 would cancel out and you will be just left with Q3 and Q1. So it basically made use of the quartiles or the interquartile range. And here, as I said just now, when it will be 0? When the numerator becomes 0. So numerator will get 0 in case of symmetric distributions, because in that case, the distance between the 50th percentile, that is median, and 25th percentile would be the same, as that of median and the 75th percentile. Okay, so this will become same as this, and that is why your distribution would be symmetric. If it is positive, it means that this quantity over here is higher than this quantity, right? If this quantity is higher, it means that you can visualize from the last figure that I just showed to you, that is right skewness, because in that case, Q3 minus Q2 would pull down the mean towards itself. So the shape of the distribution would also be right skewed. Whereas if this quantity is higher, then it would pull it down and the value becomes negative. So these are the two most common measures of skewness. To sum up, you can see this figure over here. We started with the categorical variables and we talked about proportion, count and mode.